I want to start with some animations of weather models. These are models of wind and rain, and they are used to predict the weather. They can also be used to predict the impact of weather, as you see down below, with airborne hazards like smoke from California wildfires, and on the right-hand side, coastal hazards due to storm surges and sea level rise. The mission of the National Oceanographic and Atmospheric Administration is to predict this weather in hours to days to weeks ahead of these events. And the number of events are increasing in intensity, and they're increasing in duration as well. Southwest Research is going to contribute to their mission on QuickSounder by demonstrating how we can insert technology into orbit faster and cheaper, significantly faster and cheaper than it's ever been done for NOAA in the past. So NOAA's been measuring weather on orbit for a long time. Since the late 1970s, they've been putting weather spacecraft into polar orbits around Earth. And right now, you can see the JPSS constellation or series in the middle. That's the Joint Polar Satellite System. That's what's currently delivering weather information for the models you saw a moment ago. We have hardware on some of those missions at the component level. Going forward, NOAA's building toward the NEON constellation, which stands for Near Earth Orbit Network. That's the pink series up at top. And what they're planning there is they're going to put new, better, improved resolution microwave and infrared sounders on orbit. They want to collect data faster for atmospheric weather predictions and chemistry predictions. They also want to look at ocean color. They want to be able to predict harmful algae blooms and the impacts of those on the ocean, as well as phytoplankton. So to help them in their mission, up in front you can see in the pink series there's the QuickSounder mission. That's a single spacecraft, and we're going to show them how they can take advantage of some of the commercial approaches of the last 10 years and some of the proliferation of components for constellation work at low Earth orbit that you hear about on the news. We're going to demonstrate that we can take these operational observations with a small commercial-based bus, and we can do it on a radically compressed budget and schedule. That's what QuickSounder is all about. So some of the things that they hope to learn from QuickSounder is they want to learn how to work with new space business models. These are business models that have come out of the constellation efforts of the last decade. They want to use the best commercial practices of industry. And by that, I mean they want to embrace the standards of each individual company building the components rather than try to form-fit them to NASA or NOAA's way of doing business. They want to launch in less than 3 years. And as an additional bonus, we're going to mitigate a gap in microwave sounding. There's a 5:30 a.m. and p.m. gap that will open up when some of the legacy satellites are decommissioned. So QuickSounder, in a nutshell, is going to test a disruptive procurement approach that's going to trade science for schedule. That's a direct quote from NASA. They want to cut down the cost and the time it takes to put new technology on orbit down to less than a third of what it currently is. So I want to talk for a minute about microwave sounding, what we're doing, one of the primary functions of QuickSounder. So you can see the tops of the clouds in the left-hand picture. That's a visible color image at about 18 kilometers. That's all you can see normally from a spacecraft up above. But using microwave sounders that take data at different frequencies, you can build a profile vertically through the atmosphere of where the water is and what the temperatures are. And some examples you can see on the right are water vapor at 10 kilometers down inside those clouds, independent of the temperature. And on the right-hand side, you can see the temperature, which is fairly uniform, down at 4 kilometers. So these are measurements you can take with microwave sounders, and notice that the temperature measurement is not sensitive to humidity. So there's a lot you can do vertically as you look through the clouds with these microwave sounders. Wow. So our technical approach, what we're going to do on this mission is we're going to get a legacy sensor on orbit fast. We're following what we've learned on our prior Cygnus and Punch missions. We've taken what are referred to as Class D approaches that we've helped work with NASA to develop. And some of those approaches involve embracing, as I mentioned before, commercial constellation hardware. Our intent is to get a spacecraft up into polar orbit, which you can see in the lower right is just shy of a twilight orbit around Earth, and take data in less than 3 years after they put us under contract. To do that, we're going to fly a refurbished advanced technology microwave sounder that was built for that JPSS constellation I mentioned earlier. That's an engineering model that they used for qualification testing. And we're currently modifying and building at one of our catalog spacecraft. We have a Southwest research spacecraft catalog bus that we're going to tailor to meet the needs of that sensor and then launch. So I wanted to give you a visual on how this all comes together. On the left-hand side, you can see how we designed or tailored our modular Southwest structure. What we're doing there is we're separating the major elements of the assembly so that at lower levels of assembly, things can be integrated and tested before they're delivered for final spacecraft integration. So as you bring those mechanical pieces together, we start populating the deck with commercial off-the-shelf components, reaction wheels, torque rods, batteries, things like that, things that every spacecraft needs, subsystem components that every spacecraft needs. These are pulled and tailored to mission requirements. I'm sorry, we pull based on mission requirements. We pull from the commercial market space, and we populate the deck of the spacecraft. The next thing we do is we bring our own avionics, our electrical solution, which is also modularized at the computer board level, and we do some tailoring in some targeted spaces there so that we can meet the interface needs of these components. And the punchline is, what we're doing there is in the top, we're electromechanically wrapping a spacecraft around a legacy payload. So we're taking a group of commercial sensors, commercial actuators and sensors, and we're wrapping them around the legacy payload to bring together what we call an observatory that is a little bit bigger than a washing machine by the time we get ready for launch. Then we'll be mounting on a Firefly launch vehicle, which is out of Cedar Park, just up the road, just north of Austin, and we'll launch the QuickSounder mission. The other thing we're doing as we develop this mission is we have to develop a ground system. So we have a mission operations center in Boulder, Colorado, out of that office. And we need to get this data down, and we also want to embrace the commercial approaches there. So to get actionable predictions with fast-changing weather, you need data about every half hour. You need it down. To do that, we're using 11 commercial S-band stations, so a large number of ground radios. These have very relatively small dishes. And we're using a radio on our spacecraft. The purpose there is that enables us to use a low-power radio that doesn't require any beam steering. It's a broad beam. And we take advantage of all these ground stations. And it's a very cheap solution. It's a very cheap way to get data down to the ground. So we're moving at double time. I put some statistics up there. Cygnus was our first spacecraft, and we have tailored our bus, our catalog bus, in about half the time. And we're working toward a total development cycle or a delivery to the launch vehicle also in about half the time of our previous effort. We're maximizing the use of the commercial component space, and to do that, we've been accommodating design issues and also market turbulence as we go. And I was going to give you a few examples of that. Structurally, we discovered that on a very small spacecraft, there are some vibrations, some launch vibrations that get through that are damaging and harmful to the payload. And so we're right now designing some dampers to put on a ring underneath the spacecraft. Thermally, we discovered that with a payload about the same size as the spacecraft, there is some significant heat that needs to get out. So we had to resize some radiators so we could dump heat to space. Well, the third challenge which we ran into was our launch vehicle has a tip-off rate. The rate at which we come off the spacecraft puts us into a tumble. that we can't recover quickly enough with our commercial reaction wheels and torque rods. So we increased the battery size by about 3 times and moved it to a different part of the spacecraft to take care of that. We also had a GPS radio that had a recall. They had some components that are having some issues, and they were going to insert about 6 months into our schedule, so we changed radios, and we went to a different GPS vendor. And then not long after that, our actual communications radio closed up shop and stopped making components. And so they're done. So we had to go find a new radio very quickly and work through encryption standards and a variety of other nuances to get them integrated into our spacecraft. This is why you have all that electromechanical tailoring that I'm talking about. So how are we doing so far? We've passed our project reviews, both at the top critical design review level and as well as all our lower level design reviews in the first year. We've built and certified all of our power and digital measurement equipment, which are now division resources for future spacecraft like this. And from a flight unit perspective, we've already fabricated all of our flight boards, and they're going into test right now. In the machine shop, we are building our qualification structure, and we're building our flight structure in parallel. Also another attempt to accelerate schedule. And we have an engineering test bed that we're using to test out our attitude, determination, and control components, as well as our radio right now, and work out signal issues, command and telemetry issues, and so on. So at the top level, what you see here is that we're taking qualified technical risks. We're stress testing NASA's inherited items approach. And by that, I think the shortest way I can say that is we're accepting components based on their on-orbit heritage, on-orbit performance, rather than relitigating their bottoms-up design review process. We're using that to recover a lot of schedule with the commercial-based approach. And right now, we're on target to achieve this spacecraft in about 10% of the time that it took, 10% of the cost that it took to build JPSS-1 and about 30% of the schedule. This will enable NOAA to fast track some of their technology insertion goals for the NEON series in the future, and it'll probably reset cost performance expectations as well. We have a very strong team. This is a resilient team that in 13 months worked through all those electromechanical challenges I mentioned, and everybody to the person is focused on delivery. We're going to disrupt the spacecraft development life cycle. That's what we're doing. And that way we can deliver weather measurements to NOAA at the speed weather is changing at right now. And I'll open it up for questions.